All right, thanks for joining the webinar today, folks. And I was thinking about the webinar title a little, and in some ways, the technology I spent some time working on was actually immobilizing microbes instead of mobilizing them. So I want to talk today about the N2 applied, also known as sort of the Manure Enricher. This is a technology out of Norway that uses electricity and a plasma to essentially process the manure and enhance the nitrogen content. So let me dive right in here. So this is the basic setup, and essentially what we were doing is evaluating a pilot scale system for an entire growing season at a medium-sized CAFO dairy farm. Let's see, click there. The skid in the middle is essentially the container in the middle is houses the technology, and inside there are kind of three main components. On the right-hand side is a control system and a pretty large air compressor. In the middle is actually a plasma torch, and off to the left is the black tank where you actually are processing and treating manure with some venturis on top that are doing some mixing. So I'll kind of walk you through how this all works. Essentially, step one of the process is to use that plasma torch, taking electricity to split nitrogen and oxygen molecules from the air and generate basically elemental nitrogen and oxygen, or atomic nitrogen and oxygen. These are then recombined using because they're reactive. So then they sort of recombine, and then those NOx emissions are generated. The NOx emissions are then absorbed into the manure. And in this case, what we were doing is actually doing some upstream solid liquid separation first. This unit is much more efficient if you can get sort of those coarse fibers out. Through that process of absorbing this NOx emissions, essentially, we're also acidifying the manure. And so the way this sort of works is you establish a set point pH, and it will process in kind of a semi-continuous batch until you get down to that set point, 5.0, 5.5. And through that process, the nitrogen is then stabilized primarily as a nitrate inside of this manure. And the company refers to this as nutrient-enriched organics. Really got involved in this trial from the farmer, which I think is excellent. So Mike Barnes and his family at Cobar Dairy were really interested in, what sort of new tools are out there to improve farm sustainability. He really wanted to host something so that he could sort of contribute to industry goals of reducing environmental emissions and improving nutrient stewardship. This technology has the ability to reduce methane, and I'll talk about that. It also is really increasing the amount of nitrogen in manure and, more plant available nitrogen, getting that manure N to P ratio maybe more in balance for what the crops need, so we don't have to import fossil-based nitrogen. Sort of interested in this, biocircular economy, odor mitigation, and really wanted to just say, hey, let's plug something in on a real farm instead of playing around at pilots, or at a experimental scale. So hat off to him. The farm got connected, and the technology provider N2 Applied got connected with Nutrient and brought our team in to do some of the evaluation work. So here's just some data on sort of the total solids and pH of the manure, and gives you a little bit of an idea of kind of percent mass flows. So we were pulling out of his storage, but right where the raw manure was coming out of the barn. So really trying to get that fresh manure. That went through a very small Bauer screw press. The solids then got utilized to actually grow pumpkins. And then the separated liquids went into the N2 Applied treatment system. MK 4.4 is just it's sort of a pre-generation zero pilot model number. The manure going into the system had a pH around 6.7, and the manure treated, the Neo product, had a pH of about 5.2, with no change to total solids. We then set up two different systems to really evaluate the product. We had some small static tanks and we had some flow-through tanks. And we filled one of each with the separated liquids as sort of our control. And then we filled one of each with the Neo product. The study ran from May to September in 2023. The static tanks were filled with about 800 gallons of Neo and the untreated separated liquids. The flow-through tanks were essentially being fed both materials as they were being produced. And we really worked hard to kind of balance those flows so that some of the separated liquids were going in at the same rate that Neo was in that continuous batch processing. Both systems, we installed controlled ventilation with the idea that we would have a steady kind of zephyr of air going across the surface, about 150 CFM, so that we were not creating tank conditions, but we're trying to mimic sort of an open system. And then we could take advantage of that ventilation system to measure emissions end of pipe. We monitored manure temperature and then sampled manure and emissions 3 times a week through the study period. Both myself and my team, but also working with our regional cooperative extension people, which they were thrilled to be involved in the study. This here is just showing the operation and production rates of the technology, the N2 applied system. And so we kind of had 2 different run periods. So when we first started the system in May, the unit was actually set up with a set point of 5.5, and we produced up until into July. At that point, we actually had some challenges operating the machine. We had some of the product actually generate a lot of foam and some foaming events. And so there was sort of a cleanup and reset period in the middle of the summer. And then we restarted the unit with a lower set point of 5.5 and operated it basically into the cold months here. Production rates were a little less than what was expected at about 1,000 gallons per day. That might have something to do with the fact that we used a kind of a lousy solid liquid separator. I shouldn't say lousy, wrong term, but very small, maybe undersized and not optimized solid liquid separator. So here, just getting into some of the results. On the pH side, and on the top, what you'll see is the untreated separated liquids in blue, and in gray, you'll see the nitrogen-enriched organics. So you can see in the static tanks throughout the study period, we had a pretty good difference in pH consistently until we got into the late season, and we did a few kind of post-trial samples, and we saw the pH kind of go back up. And I'll try and touch on that in a little bit. The bottom, what you'll see is in green, is the untreated separated liquids, and then the Neo product. And you can see the 2 phases of operation. And initially, we started off, again, the untreated on average throughout the study was about 6.9. You can see the Neo product, the set point was 5.5, but we ended up with 5.9 as an average. And then for the second phase, 5.0 with 5.3 as the average. You'll see after phase 1 where that pH jumps in the Neo product. And that was at the same time that we had foaming. And then in the small tanks, when that pH jumped, we had foaming. And I think what's happening is some denitrification. Not sure what triggered that, but something worth some further exploring. Looking at, kind of maybe the more interesting stuff is what this is actually doing to the manure, right? So again, we're fixing nitrogen in manure from the air. And so in the static tanks, we went from, total nitrogen on average about 0.39% to an average of 0.62%. So essentially increasing nitrogen, more than 57% in those static tanks throughout the study. And again, you see the Neo at those later stages sort of lose its nitrogen, which is, one of our indications this might have been some denitrification. If you want to sort of look at more of the agronomic measurements here, you can see that. And I think that the noteworthy piece here is most of the nitrogen that we are gaining is really NO3 nitrogen, so this plant available nitrogen. starting out from almost no poundage of that per 1,000 gallons to over 20 pounds of NO3 per 1,000 gallons. Similar story with the flow through tanks. So again, about a 53% increase. The other thing just to point out is that, P and K were relatively unchanged throughout this. Now looking at sort of the environmental, emissions here. Again, on the top static and on the bottom flow through, we basically saw about an 85% reduction in ammonia in those static tanks. And we saw anywhere from 20 to almost 100% reduction in those flow through tanks, kind of depending on which phase we were operating. So essentially getting that pH lower, we were getting more ammonia reduction and just playing with that equilibrium, right? So by acidifying, more of that ammonia is in the ammonium form and staying solubilized. Methane, also some good news there, right? So over 90% reductions in methane emissions with this technology. We had fewer data points with the static tanks, and that really just has to do with some of the challenges of measuring these gas concentrations. We had equipment that was too sensitive or not sensitive enough. And also just some complications. Our LICOR unit does get a lot of interference from ammonia, and so having some challenges getting good data with the small tanks. But generally across the study, we do see some substantial reductions in methane. That's also, there's pretty good evidence that acidifying and dropping pH can impact the methanogen populations. A couple of things that were maybe a little less desirable is that we did detect some elevated levels of nitrogen oxides, right? And so we see both of those going up in static and flow-through tanks. So those NOx emissions are a criteria air pollutant, and so that's not good. It's also a loss of nitrogen. Nitrous oxide, N2O, we didn't have a lot of data on, but the data we did have did show some increases there too. So, while we made some gains maybe in methane, are we losing that through the N2O? Some more work to be done on kind of the nitrogen gases here. Also just want to touch on energy and economics, right? So again, we're using a pilot system, and there were some real challenges integrating this European system into the US grid. The farm initially didn't have three-phase power. We brought in three-phase. It wasn't balanced enough. We kept tripping a lot of errors and faults on the equipment. That could be part of our lower production rates because we just were on and off a lot. Might also have led to unprocessed manure getting mixed with NEO, which might have led to some of the denitrification. But when we do look at some periods where we had some pretty consistent operation, we basically determined it took about 13 cents per gallon to process this material. And a lot of it has to do with that plasma torch that you can see here on the right. That really is the big energy draw here. So these systems, I think, have some great abilities, but might be best to integrate with renewable energy systems, which is some of the work that has been done in Norway so far. So just some lessons learned here, right? So the NEO does remain enriched in nitrogen and reduces emissions of ammonia and methane, at least for several months during the summer. I think, once we get beyond that, getting into the shoulder seasons, it seemed like we kind of lost some of that stability and lost some of that nitrogen. So some things to explore there. There really is the need to look at a commercial unit, right? And so the manure company, GEA, actually is connected with this company, N2 Applied now, and was developing this manure enricher. We were consulting some of their engineers. They were developing a commercial unit, and I think things have been a little paused lately. But we do hope as the commercial unit gets developed for the American market, there's an opportunity to really look at it. Some improvements to the plasma torch should really improve efficiencies. Being designed for our energy grid, hopefully things can operate more smoothly. I think unexpectedly, there's some sources of NOx emissions in N2O. Again, those things might be troubleshot a little bit with a commercial unit, but are things to look at. And ultimately, there's a need for more agronomic trials. So the farm did apply the product that was made. He did see some real, visual benefits to his crops. But the farm was not equipped with any yield monitoring data, nor did we sort of establish formal agronomic trials to really look at that side of the puzzle and really see if there's a fertilizer benefit, does that kind of offset some of this energy benefit? Um, so funding for this was supported by a SIG grant and the New York Farm Viability Institute through partnerships with Nutrient, and then our core funding comes from State Ag and Markets. And again, just want to thank the farm, Barnes Electric, who actually is no relation to the farm, but is a local electrician that did a great job with the integration, the N2 Applied folks, and my team, Lauren Ray, our CCE collaborators, and the students and interns we had involved. So with that, I think I'd pass it off to you, Bo.